In this video, we're going to look at something called Lewis structures. And Lewis structures are essentially a drawing that utilizes Lewis symbols to describe covalent molecules and polyatomic ions. One particular structure that I'm going to show how to draw here in a second is the structure of Cl2. And Cl2 is made up of two chlorine atoms, and each of the chlorine atoms' Lewis symbol is shown here, where the valence electrons are shown as dots, and it turns out there are 7 valence electrons per chlorine atom, and they have 3 sets of paired electrons and 1 unpaired electron. And when these two atoms come together to form a covalent compound, they are going to share the electron that is unpaired in each group, or on each atom. And it will form a covalent bond between the two atoms, with the other paired electrons that were with each atom still residing with its respective atom. And this particular structure is what we would call a Lewis structure. More often than not, when we draw shared electrons, we draw them as a single line. And it is possible for atoms to share more than one set of electrons. There are a few rules and terminologies and even useful techniques that we use to help us actually draw Lewis structures, and I want to talk about this just really briefly at this point. The number one rule that we need to abide by when drawing Lewis structures, at least at the beginning, because there are a few exceptions to this rule, and I will talk about those in later videos, is the Octet Rule. And the Octet Rule here is a rule that says that main group atoms, these are atoms that tend to be in groups 1 and 2, or 3 through 8, if you will, tend to form bonds to obtain 8 valence electrons. Now, I just mentioned group 8. Well, group 8 already has 8 valence electrons, so its tendency to form bonds is very low. Most often we call those noble gases or inert gases, and they won't form bonds because they already have 8 valence electrons in their outermost shell. However, the rest of the atoms do not have 8 electrons, and they will do something, either give away electrons, take in electrons, share electrons, in order to have their number of valence electrons add up to that value of 8. And that's why we call it the Octet Rule. So when we're building Lewis structures, we're going to try to count our electrons around every atom to make it to that value. And I'll show you later how to do that. The other thing is I'm going to probably use some terms that you've seen before but may or may not have associated. And that is the term single, double, and triple bonds. And what we mean by single, double, and triple bonds, I'm talking specifically about covalent bonds. And a single bond is essentially where two atoms are sharing one pair of electrons between the two, and we'll draw that as a single line. A double bond is two atoms sharing 2 pairs of electrons, and we'll draw that as 2 lines. And a triple bond is 2 atoms sharing 3 pairs of electrons, and therefore we'll draw that as 3 lines. It is possible that you might need to use single, double, and triple bonds when forming our Lewis structures, and so I just wanted you to know what those terminologies mean. There is another term called a lone pair or lone pairs, and lone pairs are electrons that are paired together around an atom in a Lewis structure that are not involved in bonding. So for instance, the structure that we drew earlier with chlorine, the 2 chlorine atoms that had a single covalent bond, right, in between the 2 atoms to connect them and share to form that covalent structure. Well, it turns out that there were 1, 2, 3, 4, 5, 6 lone pairs of electrons that were also within that Lewis structure but not involved in bonding. So just understanding the terminology of the types of covalent bonds that you might see and what the lone pairs are. The last thing will be a technique that we are going to use in order to build our Lewis structures. And this technique is called the NASA table, where NASA is actually an acronym for particular things that we're going to calculate mathematically that will go into our Lewis structure. So what I'm going to do is I'm going to show you the rule, the octet rule. Using the octet rule, we're going to place single, double, and triple bonds, lone pairs within Lewis structures, and we're going to use the NASA table. And I'm going to do that by just practicing this with a couple of examples. So let's try example 1. Let's draw the Lewis structure for carbon tetrachloride. So that's CCl4. In order to do this, what I want to show you is the NASA table. And so the NASA table, to utilize this, I write the acronym NASA in a column, a vertical column. And it turns out that each one of these letters represents a word. So the N stands for needs. The first A stands for available. The S stands for shared. And the second A stands for additional. And what we're all referring to are electrons. How many electrons does an atom need? How many does it have available? How many is it going to share with another atom? And how many does it have an additional that it's not sharing? That's what that acronym is referring to. And so in order to use it, we're going to write it in a column. And I'm going to put an equal sign next to each one of these. And I'm going to show you how to calculate each one of these letters. In order to do this, you have to do this for whatever elements are in the formula. So we happen to have carbon and chlorine. And so I'm going to make a column for each element type that is in my structure or in my formula. And what I'm going to do is I'm going to count how many I have of each. So I happen to have 1 carbon and 4 chlorines because the subscript 4 behind the chlorine element. So what I'm going to do is I'm going to use these numbers and I'm going to multiply those numbers times the electrons that are going to be calculated in our NASA table. So how we do this is we go to our needs line here and we say that we have 1 carbon, and I'm going to multiply that, and I'm going to put this in parentheses, times the number of electrons that carbon needs. And what we mean by needs is how many electrons does it need to have an octet. Well, to have an octet, that's 8. More often than not, all of your atoms are going to be 8 in this particular line or row for the needs row. There are a few exceptions to that, but you don't know what those are just yet. Watch later videos to figure out what those exceptions are. And then we're going to add that to the column of other elements that happen to be in this formula, and that's chlorine. We have 4 of those, and how many electrons does each one of the 4 chlorine atoms need? That's an octet, 8. And we're going to multiply and sum up the entire formula here. So this is a total of 40 electrons. Then we're going to go to our next row, that our available row. And what we mean by available is how many valence electrons does it have available in order to bring to the formula itself. And the valence electrons, you can go through and do your orbital diagram or your electron configuration, or you could just look at the group number of where that element happens to be. And so we're still going to take into account how many you have of each atom. So we have 1 carbon and it's in group 4. So that's how many valence electrons it has available. And then we're going to add that to the 4 chlorines and how many valence electrons it has available, which is 7. We're going to sum that together, and it turns out this will be 32 electrons. Now, to figure out how many electrons out of all the valence electrons are going to be shared, the way that we do this is we take the number that we solved for in the row N, and we subtract the value that we calculated in row A. And so that means in this particular case, this is going to be 40 minus 32. And that will give you a value of 8. And we'll just hold that number for right now. Then to solve for the additional electrons, we're going to take our available value, and we're going to subtract our shared value. So this means that the available is 32 and the shared value is 8 that we just calculated right here. And that value is going to become 24. Now, what we're going to do is we really want to use these two numbers, 8 and 4. They're the ones that are going to tell us how many bonding pairs we're going to use, or how many lines we're going to draw on our structure, and then lone pairs as well. So I'm using the term bonding pair and lone pair. And so the word pair in this means for every two. And so what we're going to do is our shared line will tell us how many electrons get shared together to form our line that we draw as a bond, a single bond. And then the additional tells us lone pair. So what we're going to do is we're going to take these two values, 8 and 24, and we're going to divide them by 2. Only do this after you have calculated all the way to the end of the additional value. Calculate everything before you divide by 2. So that way you get the proper numbers of bonding pairs and lone pairs. And this 8 divided by 2 is 4. And that means there are 4 bonding pairs in this structure. Means there's 4 lines essentially. And you can use the 4 lines to draw single bonds, double bonds, or triple bonds. It's just you're going to have 4 total. And then this additional row is 24 divided by 2, which will give us 12 lone pairs. So what we're going to use are essentially these numbers, 4 and 12. So to draw this structure, you want to keep a couple of things in mind. Typically, I'm going to give you a structure where you'll have a single element with a bunch of other elements. And we're going to need to try to draw something that connects all of these elements together in what we call the skeletal structure. In the skeletal structure, you want to keep a couple things in mind. If you have an element that's by itself, like you do here for the carbon, then that's going to be what we call our center atom. And you want to try to connect everything to your center atom, not to each other things, just to your center atom. And you want to try to draw it in a symmetrical way. And so the way that I could see this drawn, the CCl4, is 1 carbon in the center, and each one of our chlorines attached by a single bonding pair, making it to look like a plus sign. So you would have all 4 chlorines attached to the 1 carbon, and I'm taking into account I've got all the carbons represented, all the chlorines represented. It looks symmetric. And so what I'm going to do now is I'm going to take my skeletal structure, which is this guy right here, and I'm going to look at the values or the numbers that I have calculated in my NASA table. I have 4 bonding pairs and 4 lone pairs. So what you need to do is have your skeletal structure or your Lewis structure that you're trying to complete match these numbers. So there's 4 bonding pairs. Are there 4 bonding pairs? There's 1, 2, 3, 4. So if that matches, you're done adding your bonding pairs or lines within your structure. And so we're done with the bonding pairs because it ends up matching. And now what we need to do is do our lone pairs. And so turns out there are going to be 12 lone pairs. And right now I don't see any lone pairs in our structure because we haven't put any in. But there are some rules with adding lone pairs. And the first thing is, number one first, is you want to make sure that your center atom has an octet. So that means you want to make sure that it has 8 electrons, and if it doesn't, then you add a lone pair to the center atom. So we're going to look at that. So each one of these lines that is attached to carbon represents 2 electrons. So this would be 2, 4, 6, 8 that this carbon now has with it. And so it turns out the carbon is actually already at an octet, but each one of the chlorines are not. So once you go to the center atom, what you will do is then, secondly, you will go into your atoms that are connected to the center atom. So you'll start to move outward from the center, adding lone pairs to atoms that need an octet, that don't already have that. So if you look at, say, the chlorine here on the left, it turns out this line here, or bonding pair, is also attached to chlorine. So it gets to count the 2 electrons within this bonding pair as well as carbon did. And so right now, though, it only has 2 electrons. It needs 8. So to make it 8, I'm going to add 3 lone pairs of electrons to that chlorine atom in the kind of north, south, west sides of the atom, if you will. That's going to take 3 of my lone pairs out of the 12. And if you'll look, there are 3 more atoms that also fit that same criteria and need 3 lone pairs, which is 9. That's how many I had left over. And that will, if you count them all up total, that ends up being 12 total lone pairs. And with that being said, this is the completed, because you've now matched the bonding pair and lone pairs to your structure, that is the completed Lewis structure for carbon tetrachloride. Let's try doing this particular formula with nitrogen and 3 bromine atoms. So we're going to do our NASA table again. NASA, our equal sign. And then we're going to make a column for nitrogen and a column for bromine. And we're going to count. So we have 1 nitrogen, 3 bromines, and those are the numbers that we're going to use to multiply times our needs and available numbers. So we have 1 nitrogen. How many does it need? It follows the octet, so it needs 8. Your 3 bromines, how many does it need? It follows the octet, so that's 8. So this number ends up being 32. How many does your 1 nitrogen have available? That's its valence number or group number, and that's 5. Your 3 bromines, how many does it have available? And that's group number 7. And that sums up total to 26 electrons. And remember, to calculate our shared or S row, we do N minus A. And that'll be 32 minus 26, which will give us 6 electrons. Then we move down and do your last row. And to calculate that, we'll use our available minus our shared, which is 26 minus 6. And that gives us a value of 20. So now once you've calculated the last 2 rows, you go in and create pairs. So to do that, you're going to divide both by 2, and that will tell you 3 and 10. So again, what are those? 3 bonding pairs and 10 lone pairs. And so we're going to start drawing our skeletal structure, making sure that we're going to match that structure with the 3 and the 10 calculated from our NASA table. So we have 1 nitrogen. I think that will be our center atom. and then it said we have 3 bromine atoms that are connected. So I'm going to use at least a single bonding pair to connect to each of my bromine atoms, and whatever orientation I wish to do that to make it look symmetric. I could have technically taken this bromine and put it on the north side of nitrogen. It would mean the same thing. But I'm going to go ahead and I'm going to keep it the way I initially drew it here. And what I'm going to do is I've got all of the atoms represented, check. I've got all of the nitrogens and all the bromines represented and attached with at least one bonding pair. So what I'm going to do is I'm going to check and make sure those numbers are matching. So I have 3 bonding pairs here. I've got 1, 2, 3, check. I'm done adding lines or bonding pairs. Now I need to add my lone pairs. And remember, I said the first thing that you do is you check your center atom to make sure it has an octet. And it turns out nitrogen right now has 2, 4, 6 electrons. It needs a lone pair. So I'm going to just add that in the kind of north space above nitrogen because there was no bonding pair there. And so I've used 1. That means I have 9 left over. And each one of my bromines only has 2 electrons, and they need 3 more lone pairs, which will sum up to, out of all 3 of these, 9 lone pairs. And so this will look something like this, where each one of the bromines has 3 lone pairs. And that is the completed structure, because that now matches with the total number of lone pairs in our calculated NASA table with what we have drawn, and that's the Lewis dot structure for NBr3. Let's try this one more time, and this time I'm going to do an ion, a polyatomic ion. And there's one little additional trick you have to do to the NASA table to make this the calculation of the NASA table work out, but it's not much different than what we've been doing so far. So we're going to still make our NASA table as previously shown and put our equal sign. And then we're going to make a column for each of our element types. So we have nitrogen and oxygen. We're still going to count how many we have of each one of those, and it's 1 and 3. And we're going to use that in our normal calculation way for the needs and available rows. So we have 1 nitrogen, and how many electrons does it need to make an octet? Well, 8. It follows the octet rule. You have 3 oxygen. It also follows the octet, so it needs 8. And so we'll sum that up total to be 32. And then the available, what happens is we go through and do the same thing that we've done before. So we have 1 nitrogen. Its number of valence electrons it has available is group number 5. And then our oxygens, the 3, all have available valence electrons, is group 6. And so when you sum this up, this is going to actually sum up to 23. And what you should do is anytime you see an odd number, like you do right here, that should clue into you that I need to adjust this, especially if it is an ionic compound. Okay, if it's a charged compound. And so the way to do this is you're going to have to include the charge that is associated with that substance. And so this is a -1 charge. This means this substance has an additional negative electron, right? The electrons are negatively charged. So we're going to add 1 more electron, and this value is actually going to sum up to 24 now. Now, if this charge, if the charge happened to have been like -2, how many would you do? You would put +2. You add, if it's a negative charge, however many the magnitude of the number is. So if it was -4, you would add 4. Now, if it's plus, say if it was +1, then what you would do here is you would subtract 1 electron, because it's a plus charge, it has 1 less electron than what it's supposed to. Or if it's +3, you would put -3. So that's how you would work through doing that, differences in different, like whether if it's plus or minus or different values and pluses and minuses. Okay, so we've got 24 now. And so we're going to, once we've got that, that's the only difference. When it comes to ions, this is it. This is the only difference of what you have to do to calculating the number of bonding pairs and lone pairs. From this point on, we go right back to normal. So we're going to take our N minus A. That means 32, but make sure that the A is now the 24 calculated value, not 23. And this is going to give us a value of 8. And then we're going to have A minus S, and the A again is 24, and the S is 8. And so this is going to give me a value of 16. We're going to pair these, so we're going to divide by 2, and this will give us 4 and 8. So this is bonding pairs and lone pairs, which I'm going to use BP and LP for now on for bonding pairs and lone pairs. And so these are the numbers that we need to put into our Lewis structure. So let's start again with drawing the skeletal structure. And nitrogen's our single atom, so that'll be our center atom. And it turns out we have 3 oxygens. So just like the previous Lewis dot structure, I'm going to put all 3 oxygens in kind of that east, west, south quadrants below or and next to nitrogen. And I have used 3 of the 4 bonding pairs. So do y'all notice that? So we're going to check the number of bonding pairs in the structure, the skeletal structure, with the value that we calculated in the NASA table. Well, this time they don't add up. We've got an extra bonding pair that needs to be placed in the atom somewhere. Well, that means we're going to have to make a double bond. Now, I have 3 different options of places to put it because you're going to put it between 2 atoms. So I could put it between this first oxygen with the nitrogen, or the oxygen pointing down with the nitrogen, or the oxygen on the right to the nitrogen. It does not matter. You can put them in any place as long as, especially if they're all the same kind of atom coming off of the nitrogen. Just pick one and go with it. I'm going to try just kind of keeping the symmetry idea with our drawing, and I'm going to put my 4th bonding pair to make a double covalent bond on the oxygen pointing down. But again, it doesn't matter. You can put it in any location. So now our bonding pairs actually match. And what we want to do is add our lone pairs. And keep in mind we have 8 lone pairs. So what do we do first? Start with the center atom. We look at the center atom. Turns out there's 2 electrons, 2 more added up to 4. And then there's 2 pair here. So that's 4 here. So that's a total of 8 electrons that nitrogen has that it's using. So it has filled its octet and needs no more lone pairs. However, let's look at the oxygens coming off of the nitrogen itself. The single bonded oxygen on the left only has 2 electrons. It needs 6 more. So we'll put 3 lone pairs here. And the oxygen on the right only has 2, so it needs 6 more, 3 lone pairs. That's a total of 6 lone pairs, and we had 8 total that you calculated. So we have 2 more. And if you look at the oxygen here, it turns out it already has 4. So it only needs 4 more, which is our 2 lone pairs, which fits perfectly mathematically. And so I'm going to draw it like that. And so now that actually matches. Our 4 bonding pairs and now our 8 lone pairs match with the structure that we have drawn here. However, there is one additional thing that you must do to a structure, a Lewis dot structure, if you're drawing it of an ion, which is what this guy is, a charged substance. You have to indicate when drawing that structure that the structure has additional or missing electrons or whatever by showing me the charge. And the easiest way that we've found to do this is just bracket the whole structure, and then outside on the top right hand corner of the structure put the charge. And so that's how we would draw the Lewis dot structure for NO3 minus, is with the bracket and the negative charge on the outside. Okay, so those are 3 examples of how to use the NASA table following the Octet Rule and doing for neutral compounds and a charged compound. You would do the same kind of formation or format for a positively charged compound as well. Videos coming up will be exceptions to using the Octet Rule. And those include free radicals, hypervalent, and hypovalent. So check those out on the YouTube channel.